So from last lecture, we finished talking about an introduction to acids and bases and discussing some of their properties. We also defined acids and bases by two definitions. One, the Arrhenius definition we had talked about way back in chapter 7 and even in chapter 5 with nomenclature, naming acids. And in chapter 7, we really emphasize the Arrhenius definition with the double displacement neutralization reactions. And we always saw that in those double displacement neutralization reactions, our net ionic equation was essentially a proton from the acid and a hydroxide from the base combining to produce a water molecule. And then we introduced the new definition, which was the Bronsted-Lowry definition, which really focused on the transfer of the proton. So the Bronsted-Lowry definition was a little bit different. It focused on the transfer and not so much whether there was a hydroxide. So we then went on to discuss in the last lecture how at about 25 degrees Celsius, right? Because water can behave amphoterically, which means it can act as a base or an acid, depending on who's present. That water can self-ionize. And we talked about how at 25 degrees Celsius, water would basically self-ionize 2 out of roughly 10 million water molecules, right? And we would get 1 hydronium ion, and this is really how we measure acidity. The hydronium ion is just a water molecule that accepted a proton, and we would get 1 hydroxide. And basically, they would be in a 1-to-1 mole ratio. And that equation was, and you could think of it as 2 water molecules. We use the back and forth arrows because this can happen in a forward direction or reverse direction. And we would get 1 hydronium ion and 1 hydroxide ion. So there'd be 1 of each of those out of 10 million, and that's where we came up with 1 10 to the 7th. And that was important because what we see is from this, in pure water, my hydronium concentration is 1 times 10 to the negative 7 molarity. And that means essentially 1/10 of a millionth moles per liter. And because it's a 1-to-1 mole ratio with the hydroxide, we get the same. And following our rules for exponents, -7 and -7 add up to -14. And that's how we get this Kw, which is our water equilibrium constant. So that's kind of where we left off last time, is talking about different definitions of acids and bases, being able to identify which one was an acid or a base, and what are the conjugate acids and conjugate bases, and seeing that water can do this with itself. So the next step is, now that we have this constant, what can we do with it? Well, one of the things is the constant is constant. And we also discuss, if my hydronium ion increases, and it's basically my hydronium ion times my hydroxide ion equals Kw, which is always 1 times 10 to the minus 14. If this hydronium ion concentration goes up, then the hydroxide has to go down because they are inversely related. And we saw that for neutral water, the concentrations of each are equal, which is 1 out of 10 millionths. But if I was to add some acid, my hydronium ion would increase, which means my hydroxide would have to decrease. But the really thing that I want you to focus on is we have -2 and -12, and they add up to the -14. And because my hydronium concentration, 1 times 10 to the minus 2, is bigger than 1 times 10 to the minus 12, and I have more hydronium ions, this solution is acidic. And if I was to add base, so let's look at this particular example. If I was to add base, and I would increase the concentration of hydroxide, so if this goes up from 1 times 10 to the minus 7, this goes down. So, but if I look at the exponents, -8, -6 gives me 1 times 10 to the minus 14. And because the concentration of the hydroxide is greater, this would be a base. Where does it get tricky? It gets tricky when the base does not equal 1. So it gets a little trickier. And it's hard for students to see that. And it's not as simple anymore. So someone might say, well, -11 and -14 actually add up to 10 to the negative what power? Does anybody know?
15.
Yes. But if we take 2 times 5, right, what does that add up to? 10. And isn't 10 just 10 to the 1 power if we're using base 10? And what happens when I go 1, right, times 10 to the minus 15, I get 10 to the minus 14. So it still ends up being that constant. Okay. But what we're always looking for to determine if it's acidic or basic is which concentration is bigger. And what a lot of people get confused is they look at this 11 and they think, well, that's a bigger exponent. But remember, it's a negative value. So it's actually smaller. This -4 is much closer to 1 molar. Now, I could do a really quick and easy one for you, and you guys will be able to figure this out right away without really having to use your calculator. So if I told you your hydronium concentration was 1 times 10 to the minus 3 molar, you could figure out your hydroxide really easy. And why is that? Because that's a base 10. 1 is a base 10. That'd be like saying 10 to the 0. Does anyone know what the hydroxide concentration would be? If my hydronium was 1 times 10 to the minus 3?
1 times to the -1.
11.
It'd be 1 times 10 to the negative 11. Exactly. So if this was a problem, if I said my hydronium ion concentration is 1 times 10 to the minus 3, what's the hydroxide concentration? What am I using? I'm using Kw. It has to add up to what? 10 to the minus 14. That's what you did. You said, oh, this exponent and this exponent add up to 14. But these bases have to be in terms of base 10. They basically have to be a 1 because 10 to the 0 equals 1. Right? In this case, it's a little trickier. You might have to use your calculator. All right? The other thing that you should be able to do is to determine, based on these concentrations, what it is. Is it neutral, acidic, or basic? So right off the bat, we can cancel out this is not neutral. It's not neutral because they're not in equal amounts. So to determine whether it's acidic or basic, we have to see and decide which ion concentration is greater. So which concentration is greater? Is 1 times 10 to the minus 3 bigger than 1 times 10 to the minus 11?
The hydronium concentration is higher.
Negative, yep. So the hydronium, the -3 exactly, is a bigger number. So that means I have more hydronium. So is this acidic or basic?
Acidic.
Exactly. Because we're measuring the acidity based on that hydronium concentration. So why is this powerful? Well, now we can do calculations. We can determine whether a solution is acidic or basic. Now, I should have really just put C in the beginning because this is the easy one, right? This is easy. Why? There's a 1 there at base 10. So I know, and this is -7. So my hydroxide has to be 1 times 10 to the minus 7. And because these are equal, that makes C what?
-7.
Well, yeah, it makes a hydroxide 1 times 10 to the minus 7, and it makes it a neutral solution.
Neutral.
Neutral,
Yes.
yeah.
Right. So we don't have to do calculations to figure out which one's acidic or basic. So like A, I don't have to do a calculation. 10 to the minus 5 is going to be bigger than 10 to the minus 7. So this is going to be acidic. So right off the bat, I know this is acidic. Because 10 to the minus 5 is bigger than 10 to the minus 7, which is neutral. So there's more hydronium, so it's more acidic. And then when I look at 10 to the minus 9, well, that's smaller than 10 to the minus 7. So it's got less of what we measure acidity than a neutral solution. So this must be basic. And you can always double check how. Well, they might ask you to calculate hydroxide. And how are you going to calculate hydroxide? Well, we already said Kw is hydronium plus my hydroxide. So to solve for hydroxide, just take the value of Kw and in your calculator, divide it by the hydronium concentration. And you get your answers. So the hydroxide for A, right? I take Kw, I divide it by the hydronium concentration, and I get 1.3 times 10 to the minus 10. And now it's obvious that this number is much bigger than that. So it's acidic because my hydronium concentration is greater. What about the next one? So again, I'm dividing by my hydronium ion to get my hydroxide, and I get 6.7 times 10 to the minus 6. So in this case, the hydroxide concentration is bigger, and that's how we measure bases. So that's basic. And in C, it's neutral. So it's pretty easy to figure out if something is acidic or basic. All we need is Kw and this relationship right here, right? So you can determine based on whether the hydronium concentration or the hydroxide concentration being bigger, whether it's acidic or basic, okay? But there's actually a way to, there's a measurement, there's a scale for that, and it's called pH. So it has values ranging from 0 to 14. If it's acidic, the values are between 0 and 7. If it's neutral, the pH is 7. If it's basic, they're greater than 7. So really, you could think of pH, and I tell students, it's almost like a pH 3.0 plus, because what you're doing is you're measuring a relationship with that hydronium ion. Right? So here in the middle, pH 7 neutral. All the way to 0 is acidic. If I go from 7 to 14, that's basic. Strong bases are 12 or greater. Weak bases are between 7 and 12, especially 7 and 10, right? Strong acids are 2 or less. Weakly acidic is from 7 to 2 or even down to 4. So this scale can quickly give me a number that I can identify, is this an acid or a base? And I can do this without looking at exponential notation. So it's easier, it's very user-friendly. You know, it's not as intimidating as some number times 10 to a negative power. But again, how do these relate to each other? Well, it goes back to what we said earlier, right? At a neutral pH of 7, the hydroxide concentration and the hydronium concentrations are equal. As I increase the hydronium concentration, the hydroxide concentration decreases. but they still always add up to the constant Kw, which is 10 to the minus 14. Now at pH 0, we see that the exponent is no longer, a negative integer. It's a 0. And what that comes out, 10 to the 0 is 1. And basically your hydronium concentration is a 1 molar. And then it works in the opposite direction. If I get less and less hydronium, then my hydroxide goes up. And that means I'm more basic. But it still always equals that constant. So when there's a ton of base, a 1 molar base solution, there's very little hydronium. Oh, whoop. So now remember in lab, in a lot of your fume hoods, you were looking at things like 3 molar H2SO4 or 6 molar HCl. So that's 6 times more concentrated than that. So that's actually a pH that's negative, but we don't really go into that. But I just want to let you know, you can have a stronger acid than a 1 molar concentration. Okay? But this is the scale we're using. The other thing you have to understand is to make the pH an easy number, how do we take 1 times 10 to the minus some number and make it an easy scale? We have to take the negative log. And the reason why we're doing log functions, and again, you might want to get your calculator, is this exponent is using a base of 10. And on your calculator, when you use log, it's base 10, right? So like if you were to go log and then hit 100, on your calculator, you would get 3. Why? Because log is a base 10, and 10, oh, actually, I said 100, 1,000, sorry. 10 cubed would be 1,000 in exponential form. So the log is basically taking exponential form and converting it, right, into an easier number for us like that, basically an exponent. So how do you do that? Well, if you have the hydronium concentration, you can plug it in directly. So pH is negative log whatever your hydronium concentration is. But what you have to understand is it's a log scale. So 1 unit on a pH scale is actually a concentration of 10 times. So if I had 1 times 10 to the minus 1 molar for my hydronium concentration, that would actually equal a pH of 1. But if it was 1 times 10 to the minus 2, my pH would equal 2. So this is a, one difference in the pH scale, but in concentration, it's tenfold. And why is that? We're using log, which is base 10. So it's a different type of math. It's a different operation. So because it's a different operation, right? We had rules for the operations of addition and subtraction, and then we had rules for multiplication and division. We have new significant figure rules. So it brings it back. So what are the Sig Fig rules for, this is missing a negative, for pH? Whenever we use log functions, whatever number you're using, right, for your concentration, this is how you're determining your sig figs, right? So if there's 2 sig figs in your concentration, once you calculate your pH, you use the sig figs after the decimal. So in this particular calculation, there's 3 sig figs. So I go 3 sig figs after the decimal. So whenever you deal with going from concentration to log, the log sig figs go after the decimal. So for, let's say, this particular, what is the pH of coffee if the hydronium concentration is 1 times 10 to the minus 5? This is pretty easy, right? Because I don't even need my calculator. I know that, you know, if I take the negative log of this, right? So pH equals negative log 1 times 10 to the minus 5. When I take base 10 into account, that exponent gives me a negative 5. So the negative in front of the negative log function cancels out, and I get a pH of 5. So really, I'm looking at this exponent right here to figure out my pH if it's base 10. So this is pH 5.0. And the reason why it's 5.0, there's 1 sig fig here. So I go what? 1 sig fig after the decimal. But that's a really easy one, okay? And we also see that this is acidic because it's a concentration that's greater than 1 times 10 to the minus 7, and the pH is less than 7. Let's do one that's a little trickier. So I'll give you guys, I don't know, maybe 2 minutes. You can put it on your calculator and see what you get for this one. So you're going to be using pH equals negative log hydronium concentration. So you should try to do this on your calculator. What do you guys get?
3.7.
Good. And it is 3.7. And so we're going, there's 1 sig fig here. So we go 1 sig fig after the decimal. Now, a lot of people might say, well, wait, this is, you know, 10 to the minus 4. Why isn't it 4? Because that's not base 10. And I try to explain this, and some students normally get this. Not everybody does, and it's okay, because you can always use your calculator. But you can kind of figure this out. We know it's not going to be 10.3, because that's basic, and this is acidic. This is 10 to the minus 4. But, you know, which one of these is it? Well, if you look at it, right, if I add 1 times 10 to the minus 4, and 1 times 10 to the minus 3, right? This is a pH of 3. This is a pH of 4. Really, I could kind of rearrange these and say, you know, this is still 1 times 10 to the minus 4, but this is like saying 10 times 10 to the minus 4. And why is that? Well, 1 plus negative 4 equals negative 3. So really a pH of 3 is like saying if I want the exponents to be the same so that I can compare, it's like saying 10 times 10 to the negative 4 if you want to do that instead of 1 times 10 to the minus 3. You don't have to, I'm just giving you something. And then pH 4 is 1 times 10 to the minus 4. So why am I saying that? This number 2, is 2 closer to 10 or closer to 1? Now that's not a trick question. Anybody? Is 2
It's closer to 1.
It's much closer to 1. So what does that mean? That 2 times 10 to the minus 4 is much closer to the 1 than the 10 times 10 to the minus 4. So it should be closer to the pH 4. So 3.7 makes sense. Now, a lot of people might say, well, why is it 3.7 and not 3.5 or something like that? Remember, the log scale is base 10. It's a tenfold difference. But I'm just trying to have you be able to look at numbers and make sense out of it using exponents. So I'm going to let you guys work on these problems. So I'm writing some things down, right? Now, you may not believe this, But there is something, and people don't know this, there is something called POH. Does anyone want to take a crack at what POH? How you can figure that out? It's a log function. Whenever you see that P, it's a log function.
Would it be the negative log of the OH minus?
Yeah, exactly. It's a negative log of the OH minus. So there's actually a POH, there's a POH. And there's different ways you can get it. You can do the OH minus and do the negative log of it. Or if you have the pH, pH plus POH equals 14. Why? Because of KW's exponent. But let's solve these problems. So this first problem, pH. Well, if they want pH and I have hydronium, that's easy. Negative log hydronium equals negative log 1.8 times 10 to the minus 4. What did you guys get?
3.7.
What is it?
3.74.
3.74. Now, does this make sense? Yes, it does. Why? We have 2 sig figs. So what do we do here? 2 sig figs after the decimal. We just got done saying that 2 times 10 to the negative 4 was 3.7. And 1.8 is almost 2. So this is almost 3.7. It's 3.74. It's just a little more precise. Excellent. So is this acidic or basic?
Acidic.
Yes. Right. So I'll erase, what I wrote because it's kind of covering everything up, but I like to write it out for you. Now for this one, right, what could we do to get the pH? So to get the pH, right, we know it's negative log hydronium. How could I get the hydronium concentration? What could I use to get the hydronium concentration? And so how could I get this from this? Can I use KW? Isn't that what we did before we even did pH calculations? Right? So what did I do to get the hydronium? I basically said, well, my KW is hydronium times my hydroxide. So hydronium is just my KW divided by my hydroxide. And that's what this is. 1 times 10 to the minus 14 KW. My concentration is 1.3 times 10 to the minus 2. Goes there. And now I get a concentration for my hydronium. And what can I do now? Plug it into the negative log, and I get 12.11. Now, I haven't asked, but in both of these problems, I could ask what your POH was. And how do I do that? Well, I said it earlier. pH plus POH equals 14. So if this first problem, if I wanted to figure out the POH, I would just say 14 minus the pH, 3.74. So when this top problem, and I'm going to erase some things because I'm kind of running out of room here, right? It would be a 10.26 POH. What would the POH be in this one?
Would be 1.89.
Exactly. So the quick and easy way is just take this and subtract it from 14. And you get 1.89. There is another way. You could do the POH by just doing the negative log of the hydroxide. But why deal with another log function if we already have pH? What you could have done is gone from hydroxide concentration straight to pOH and then worked back that way. But there's more than one way to solve this. And you'll see that on the homework problems. So now we're going backwards, right? So we know from pH, it's negative log hydronium concentration, okay? Well, the logarithm has an inverse function, okay? So what do I mean by inverse function? You can think of it as kind of like an opposite operation. So like for addition, the opposite operation would be subtraction. For multiplication, the opposite operation would be division. So in algebra, you learn that the inverse operation, the opposite operation of logs, are exponents, right? And that's kind of why I showed you that earlier. So for pH, which is a negative log hydronium concentration, we could rearrange this and we get that the hydronium concentration is just 1 times 10 to the minus whatever your pH is. Okay, so if your pH is a really easy number like 8.0, right, then your hydronium concentration is just 1 times 10 to the minus 8 molarity. That's easy, okay, because it's just a integer. Okay, that's easy. Now, where is it more difficult? Oh, and this is showing you how to do it on your calculator. So to enter the pH value, you're going to do negative whatever your pH is, okay? And there's an inverse function key. So if you look at your log button on your calculator, so that's one of the things I said before I even started lecture today in the first couple minutes. If you take your calculator out and you look at the log button on the calculator, typically in blue or yellow, right above the log button, there's a 10 to the x, and you have to hit that second function, the either yellow or blue button that says second. So when they say use a second function key, so basically the way you would do that is if you wanted to do hydronium concentration, right, you would hit your inverse second function key, and then typically you would hit what's called the log key after the second function key, because above log, you should have something like that. And what that will do is it'll put it, when you do that, it's thinking it's 1 times 10 to the negative, and then you're going to hit, right, the negative 8. So you have to make sure to hit that negative. And then you're going to adjust the significant figures. So again, with pHs, because it's a log function, there's 1 sig fig after the decimal. So your final answer should have 1 sig fig. So the concentration only has 1 sig fig. Again, it's really easy if it's an even number, right? So if I had my hydronium concentration, you know, what is it if it's a pH of 4.00? Well, that'd be easy. It's 1.0 times 10 to the negative 4. Why? I'm just taking the negative value of this, putting it in that exponent, and for sig figs, there's 2 after the decimal and 4.00, so there's 2 for concentration. But you're not always going to get perfect pHs of integers. You're not going to get 8s or 4s. We just saw in those last problems, we had a 3.7, and then we had a 3.74, and then we had a 12.11. So like before, if you don't have these perfect integers, that's when you really need to use your calculator and that 10 to the x key, the inverse function. So I'll give you guys a minute to calculate this. I'll put the screen on pause and see what you get. So what did you guys get?
1.6 times 10 to the negative 4.
1.6 times 10 to the negative 4. Everyone agree with that? Numerically, it totally makes sense just looking at it. So Sam probably did what we've been talking about. To figure out the hydronium concentration, she knew it was 1 times 10 to the minus pH. So how did she do that? She probably hit the second function key on her calculator and then hit the log button, which is really a 10 to the x, and then hit a negative 3.80. And then hit equals and got that value. This value totally makes sense. Why? 3.8 is between, again, 4 and 3. It's much closer to 4. So 1 times 10 to the minus 4 would give me a pH of 4, or 10 times 10 to the minus 4, which is really equal to 1 times 10 to the minus 3, would give me a pH of 3, and 3.8, right, is much closer to 4 because 1.6 is much closer to 10 or to 1 than it is 10. So this totally makes sense. And she also did 2 sig figs after the decimal because we're using pH, which is a log function. So her concentration was in 2 sig figs. So that's perfect. And I apologize, I wrote over all the writing, but I like to. So you get this big, you know, kind of hideous number, right? That doesn't look, that's a typo right there. Yeah. Huh. I'm sorry, this is a typo. It's 10 to the minus 4. But she knew she needed 2 sig figs, so she went 2 sig figs, saw the 8, and rounded it up. This is a typo. So what did you guys get for your answer for this particular problem? Anybody?
1.4 times 10 to the negative third.
Okay. Okay,
Could you walk us through it one more time?
sure. So to do this calculation, right, from pH, to figure out your hydronium concentration, right, it's basically 1 times 10 to the negative pH. So that's why I said it looks like this, but you don't want to leave your exponent in a decimal form. So the way you would do it on your actual calculator, it really depends if you're using a graphing calculator or not. So if you have a graphing calculator, it's a lot easier on a graphing calculator. On a graphing calculator, you would literally hit your second function, and then you would hit that log button, which puts it to the 10 to the x, and then you would hit negative, and then you would do the 2.85. Now, let me do it on mine because I have a non-graphing. I want to make sure that, and actually with my TI-30, I can do it the same way. I can hit second function log and then hit the negative 2.85 and then hit equals, and I would get that. So after this, you would hit equals. I actually get, 1.41253 times 10 to the negative 3. There's 2 sig figs after the decimal, so I only want 2 sig figs, so that's why it's 1.4 for the concentration. But I don't know, Lauren, your calculator might have you input it differently. Did that work when you hit it this way?
Yeah, I got it. I just had my my calculator wasn't in scientific, so it was confusing me.
Oh, okay.
But after I changed it,
Okay.
it makes more sense. Thank you.
Yeah. Well, on my calculator, actually, when I hit enter or when I hit equals, it didn't put it in scientific, it didn't put it in this notation for me. I actually ended up getting 0.00141253. And I just converted it to scientific notation just to make it, resemble these answers. But we
Right.
could still use our rules for scientific notation that we learned in, the first week when we were talking about the metric system and how, because things are so small, we get really big numbers and vice versa. So if you follow your rules for exponents, this number is less than 1. So that's why you're going to have a negative exponent. And what should the value of the exponent be? 1, 2, 3. Remember, you go after the first non-zero digit, you're going to the right. That's why it's a -3 exponent. And it's, again, the 1.4 times 10 because we're moving it to the -3 3 times.
Okay.
Make sense?
Yeah, I was just thrown off because I was seeing a decimal.
Yeah,
But
and I mean,
I understand.
yeah, a lot of calculators will do that. They won't put it in scientific notation. The other thing is some calculators don't let you enter it the way I just wrote out. So that's why I was asking you if it worked, because some calculators you have to work backwards. Some calculators you actually have to hit 2.85, then a negative, then you have to hit second function log, and then equals. So sometimes you have to work backwards. It depends on the calculator. But yeah, if you can do it this way, left to right is always easiest.
Okay.
Awesome.
That's good.